Okay, folks, welcome back. This will be the last video in our series on electrochemistry. And today we're going to talk about Faraday's laws. Really summarizing or getting to the heart of the research that was done to determine how the mass of a material, whether it's being plated on, think about like plating silver onto a trophy or something like that, or chrome onto motorcycle parts, and the amount of current that has to flow through to make that happen. So there is a stoichiometric relationship between these values. And I think we've already started to see that in thinking about how many electrons or how many moles of electrons have to pass for one set of a balanced electrochemical reaction to happen. If we can then relate the number of moles to the charge that passes and also to the mass of the material, then I think we've done something quite powerful. Okay, so let's begin by thinking about that and exactly where we're going to get these relationships formed. So, excuse me. So first, we're going to say that just summarizing Faraday's laws, one being the mass of a given substance that's produced or consumed at an electrode is proportional to the quantity of electric charge passed through the cell. Great. So if it's proportional, we don't exactly know how yet. But there is some relationship between the change in the mass of an electrode and also how much electricity or how many electrons have passed through that cell. Okay, number two, so equivalent masses of a different substances are produced or consumed at an electrode by the passage of a given quantity of electric charge through the cell. Again, great. So this takes us back all the way to first week and thinking about how mass versus number of atoms of things and how that compares to each other. So again, we can tie this back to stoichiometrically balanced chemical equations. What we're going to need to do there, since we're talking about the quantity of electric charge through a cell, is think about the charge on an electron and then scale it up. So charge on a single electron, we've already said, is 1.602 times 10 to the negative 19 coulombs. So this is also called the fundamental or elemental charge, elementary charge. Of course, for an electron, it's going to be negative, but we're really just looking at the amount of charge here. Charge represented by a mole of electrons. So in order to do that, we're just going to have to take this number, 1.602 times 10 to the 19, negative 19 coulombs, and multiply it up by Avogadro's number. So if this is the charge on one electron and we want a mole of electrons, so we'll multiply that and we get 96,485 coulombs per mole of electron. And this is Faraday's constant, which we've been using all along, but this is again why we call it Faraday's constant, because he was the guy doing this work. And again, often you'll see this kind of as a fancy F, but given how unreliable this screen has been so far, we're just going to keep writing it as an F. Okay. Okay, so now we have the charge on a mole of electrons. Good. So how are we going to relate that to the amount of electric current that's flowing through the circuit? So electric current, usually called an I. This is the amount of charge, so Q as in amount of charge. Again, we're seeing Q. No, it's not heat. No, it's not the products over the reactants. It's an amount of charge. And we said it's per unit time. Okay. So seconds, if we're going to use the SI units, which we are. So the units are in amperes, or often called just amps. And it gets the capital letter A. And an amp is worth 1 coulomb per second. Okay, so this is again charge per unit time. Okay, so if we have a current of I amperes flowing for T seconds, so this will say we have so many amps flowing for so much time. So this is going to give us an amount of charge that's passed through. because we would say coulombs per second multiplied by seconds. So now we'll just have an amount in coulombs. And if we take that amount and then divide it by Faraday's constant, which is coulombs per mole electron, we end up with moles of electrons. So this is the number of moles of electrons that pass through the current based on the amperage. And now we can take that moles that actually pass through the real current, through the real circuit, and relate it back into our balanced chemical equation to see, to compare it to the moles of substances. So the moles of copper that was reduced, or the moles of zinc that was oxidized, since we've used those probably more than any other metal. And of course, if we then know the moles of copper or moles of zinc, we can just take their atomic mass, their molecular mass, and figure out exactly how much mass of these things that we've deposited. Okay, scrolling, here we go. So this relationship lets us go from something that we can measure with a multimeter, so amperage. If we multiply that by the time that current was flowing, so this would be times the time, it gives us an amount of charge in coulombs. If we then divide by Faraday's constant, then we get moles of electrons, which we can then use through our balanced reactions. Half reaction, full reaction, we're still going to get the same amount of substances. Okay, to get the amount in moles of the metal or the ion that we're interested in, and then finally into its mass by converting from moles to grams. Okay, so let's try this first example. A little slightly easier one to get us kicked off. So we have a 6-volt battery delivering a steady current of 1.25 amps for a period of 1.5 hours. We want to calculate the total charge in coulombs that passes through the circuit and the electrical work done by the battery. Okay, we'll address that last one at the end, but let's just see what the question gives us first. Okay, so first we have the cell potential is just given for us at 6 volts. 6-volt battery means a potential of 6 volts on the cell. The current that has flown is 1.25 amperes. Time gives us 1.5 hours. And we're just going to multiply that by 3,600 seconds per hour to get the amount in seconds, since we want to keep it all in the standard units. Okay. So the total amount of charge that's flown through is just the current multiplied by the time. So at 1.25, well, coulombs per second, amps, same thing. Okay, multiplied by 5,400 seconds gives us a total amount of charge of 6,750 coulombs. Okay, so that was the first part of the question. So we wanted to know the total charge in coulombs that passes through the circuit. So there's first part answered. And now we want the electrical work done by the battery. So how we're going to find work done by the battery is to first think about what's going to let us access an amount of work. Remember that delta G, or the Gibbs energy of a reaction, is equal to the maximum amount of work accessible through that reaction. And we also have a relationship between the cell potential and the charge that passes through the reaction back to delta G. So we've been writing it recently as moles of electrons times Faraday's constant times the cell potential. But you'll also remember that that first part is just the charge. So we can use the charge we've already calculated. So 6,750 coulombs multiplied by the cell voltage to give us, oh, sorry, this should be a negative Q. So we have a negative in here. So negative 40.5 kilojoules per mole. Okay, so that's, or if we like, just kilojoules was the work done during that process, during that time. Okay, so the steady flow of 1.25 amps at 6 volts for 1.5 hours gives us, lets us access 40.5 kilojoules worth of work. Okay, so what are we going to do with that work? Various things. We can talk about plating silver, which is, I think, where this first question is going to take us. If I'm able to scroll down the page to it. Here we go. Okay. A galvanic cell. So this, again, galvanic cell tells us right away that it's going to be spontaneous and that delta G is going to be negative, and it means that we can access work from it. Okay. Is assembled in which silver ions in silver chloride are reduced to silver, and copper metal is oxidized to copper 2+. Okay, so we already have our cathode and anode laid out for us. What else we got? A current of 0.5 amps passed through the cell for 101 minutes. Calculate the mass of copper consumed and the mass of silver deposited. Okay, so as per usual, what we would like to do is start with the balanced equation. So we know that we're going to take silver ions in solution, and they're going to be reduced to silver metal. Okay, so that silver is going to get deposited. The silver ions are going to get reduced. And to balance the charge on this equation, we're going to have to add an electron onto the reactant side. And we're good for the cathode, since it's being reduced. On the anode side, it says copper metal is oxidized to copper 2+ ions. So let's write it out. Copper is being oxidized to copper 2+. And again, we know to balance the charge, we're going to need to add 2 electrons onto the products here. And that is our anode. Again, that makes sense. Okay, if copper is getting oxidized, it's giving up some electrons. They're being picked up by the silver. Of course, to balance this properly, we're going to have to make sure that the moles of electrons are equal in both half reactions. So we can go ahead and multiply the top line by 2. So we have 2 electrons, and now we also have 2 moles of silver for every mole of copper that's being oxidized. Okay, so we have our balanced equation, but calculate the mass of copper consumed and the mass of the silver deposited. So in order to do that, we're going to need to know the amount of one of the actual number of something in these reactions that gets used, right? So what we're doing with electrochemistry is saying, well, if we know the current and we know the time, then we can determine the moles of electrons that actually pass through the circuit. And if we know the moles of electrons that were actually used, we can use that by stoichiometric balance to say how many moles of copper and how many moles of silver are also produced. Okay? So first, we want to know the number of moles of electrons. And what does it say to us? Okay, so we have the amount of charge. So this is the current multiplied by the time. So this is 0.5 amps multiplied by 101 minutes. And we'll get that into seconds. So it's going to be 60 seconds per minute. And this gives us 3,030 coulombs. Okay, so to turn the charge into the moles of electrons, well, that's what Faraday's constant is for. So let's go 30 coulombs times 1 mole of electron per 96,485 coulombs. And this tells us we have a total of 0.0314 moles of electrons. Okay, so with that, Now we can take that and work with our balanced equations to say, well, if we only passed 0.314 moles of electrons through the circuit, how many moles of silver is that going to leave us with? So let's start with the silver. And we'll just take a note before I scroll too far down the page, that if we have 0.0314 moles of electrons, and we want to convert that into moles of silver. So let's go moles of electrons on the bottom, moles of silver on top, so we make sure that we get our units correct. And then we can look back at our balanced equations to say, well, how many moles of silver are we getting for every mole of electrons? So in the balanced equation for silver, 2 moles of electrons leaves us with 2 moles of silver. So that's really just 1 to 1. And we end up depositing 0.0314 moles of silver. But of course, it doesn't ask us how many moles of silver we deposited. We want to know in grams. So take that same value, 0.314 moles of silver now, multiply it by its atomic mass, so 0.727 grams per 1 mole of silver. And we end up with 3.39 grams of silver was deposited by running a 0.5 amp current through the cell for 101 minutes. And it's going to be exactly the same process for copper. Okay, so if we have 0.0314 moles of electrons, and now we need to say, okay, well, how many moles of copper are we getting per mole of electron? We can have a look at our balanced reactions again, and we're going to find eventually, okay, that we have 1 mole of copper for every 2 moles of electrons. So we'll take that back down the page and say, okay, so 1 mole of copper per 2 moles of electrons gives us 0.0157 moles of copper, which again, we take that 0.0157 mole of copper multiplied by, what do we have? It's 63.55 grams per mole of copper. And we end up with 0.998 grams of copper was dissolved in order to deposit 3.39 grams of silver, okay? And those ratios would stay the same even if we change, if we left the current running longer, for example, or we use a different amperage, we'd be running with more charge. Okay, so take a moment, I guess, to catch up with those values as I fight to get back down the screen. And we'll move on to our second example. Okay, in this case, we know an amount of metal that we want to deposit onto, what are we depositing onto? A faucet. Okay, so we're plating a faucet with chromium metal by electrolysis of aqueous, let's see, chromium sulfate. If 12.5 minutes are allowed for plating, what current is needed? So how much current do we need to run through this circuit in order for this scenario to work? So first things first, let's do the equation for breaking up this salt in water. Okay, so Cr2, SO4, 3. Okay, so we can see that we have the anion as the sulfate. We're going to get 3 of those, SO4. And the charge on this, either you'll have to look up or just sort of think about it by comparison. We could do the full breakdown of the oxidation rules to get you there. Okay. The other thing you might recognize this SO4 from sulfuric acid, where we usually say it's H2SO4. If it carries 2 hydrogens to get to a nuclear to a neutral molecule, then we know that it's going to be 2- on the backside. Okay. And if that's a 2- charge and there's 3 of them, it's in total going to bring it down to -6. That means that the chromium has to do the work to bring it back up to neutral. There's 2 of those, so we'll have 2 chromium ions at a +3 charge each. Okay, and that's going to balance out the salt, gives us the neutral salt, and also tells us what we have in solution. In order to then reduce this chromium, so we want to take chromium 3+, chromium 3, and reduce it into chromium metal. Balance the charge on that, we're going to need 3 electrons. Okay, so it wants to be up there. We got 3 electrons. Wow, all right. Going to be able to do it? I doubt it. Okay. 3 electrons, please. 3 electrons, okay. Plus chromium 3 to chromium metal. Okay. If we don't touch it, maybe it'll keep it going. Okay, and this is going to be, of course, our reduction half cell or the cathode. Okay, but I don't see anywhere listed there what's going to be working as our anode. So something has to be oxidized in order for this to get reduced. And where is our oxidation? In this case, it's water. Okay? The water itself is going to be oxidized into oxygen gas. So if we have water oxidized to oxygen, we're actually going to have 2 waters, and we're going to be left off with 4 protons and also 4 electrons. So there's our oxidation step. What happens to these guys, by the way? So since we already have the sulfate in solution, this is going to react with 2 of those, 2- to turn into that sulfuric acid, okay? Which of course is going to work in equilibrium with water to end up with some amount of H3O plus and also HSO4 minus, okay? So there is going to be some balance. You know, in the end, it's going to be more acidic, but here we go. Okay, so all that to say, what do we want to do with this, this chromium? So we want to plate 0.86 grams. This is from the question, 0.86 grams of chromium. Let's convert that into moles so that we can actually work with our equations. Okay, times 1 mole per 51,996 grams chromium. So this is giving us 0.0165 moles of chromium. Okay, and so since we actually, what we want to know is the moles of electrons being transported recorded here, since we do want to get back to a current that we need. Okay, so this is going to be our 0.165 moles of chromium. And we can do how many moles of electrons do we get or do we need to produce each mole of chromium. From the balanced reaction, we saw that there had to be 3 moles of electrons per 1 mole of chromium. And this will end up being a nice round number, 0.05 mole of electron. So now that we have a moles of electron to find the current, which is what the question is actually asking, this is the charge per time, which is also, we've said, is the moles of electron times Faraday's constant for charge, still divided by time. And here now we can finally fill in all the numbers we need. So 0.05 moles of electrons multiplied by Faraday's constant, divided by, and it gave us 12.5 minutes. And of course, that's 60 seconds per minute. Will all work out to a final answer of 6.4 amps. So this is an example of where, say if you were trying to do this as an industry, what's cheaper, your time or the amount of current that's flowing through the process? Also, we haven't talked about how much this is going to heat up. You know, if you crank up the amperage on something, you put some more power through it, you're going to eventually run into some other problems, either with heat or with destroying your electrode. It's really going to depend on a bunch of other physical properties that we're not taking into account with this question. And then also, what is the electrical company charging you per, say, per amp coming into the system versus how many faucets you can put out per amount of time as well. So if we're thinking of like an engineering problem, it's going to be balancing quite a few different variables. And this is one of the ways when we can start to see, okay, there's a difference between, or a relationship between the amount of time we want to spend on it, the amount of electricity we want to spend on it, and the amount of material we finally want to get on the faucet. Okay, so that's electrochemistry. That's all of the course content for that. For more questions, we're going to have some more worked problems coming out in the future. In the meantime, check out your textbooks, find questions that are listed as Nernst equations, problems, Faraday problems. Just go through them, try them before you check out the answer, just to make sure that you actually know what you're doing and aren't fooling yourself. And in the meantime, we're going to start next on some organic chemistry principles, polymers, proteins, and biomolecules. So I hope to see you then. Okay, thank you very much for watching.